Okay, we're going to continue here, chapter 15. So in this chapter, we were talking about KSP, which is the solubility product. It is, again, as we talked about, basically an equilibrium constant for things that are typically insoluble. So these are for guys that, as we talked about, if you look at sort of the solubility rules, we typically think of them as being insoluble. So for example, something like silver chloride, which again, based on solubility rules, would be insoluble. But as we talked about, anything that technically is insoluble does have some degree of solubility, even if it's really, really small. So even though we typically think of this guy as a solid, it will in solution dissociate a little bit into ions. And because of that, it will set up an equilibrium. And we can write our KSP expression, which would be like normal, so our products over our reactants. But typically speaking, in KSP problems, this is typically how all the reactions are pretty much written. Usually you have solids on the left-hand side, and you have your aqueous ions on the right-hand side. So usually we'll have just the products when you write sort of the expression here for the KSP. We also saw or talked about that KSP values are typically very small. And what that means is, like normal, it's an equilibrium constant value. So if it's really small, that means really when we reach equilibrium, we mainly have reactants, which is why it's considered still to be pretty much insoluble. But we have a little bit of those free ions that are floating around. So there's really sort of two types of almost sort of KSP type problems that we talked about. One where you, for example, are given the KSP value. And for that, you would do an ice table like we talked about. These ice tables are a little bit different in terms of we do typically use a different letter. We oftentimes will use S instead of X. It doesn't really matter. You can use any letter you want. But again, here, the S does represent usually the molar solubility, which is the molarity. And then we do solve it just like we do a normal ice table. We would obviously put our equilibrium sort of expression, our values into our KSP expression. We would solve for S, and that would give us our molar solubility for it. If we wanted solubility in grams per liter, we talked about basically when you do solve for S, that is basically our moles per liter. Using our molar mass there, we can kind of go from moles to liter to grams per liter, which is, again, a very common sort of solubility sort of units that you end up with, is how many grams you can dissolve in a liter. The other type of problem is one where they do sort of maybe give you the solubility of the compound in whatever units, grams per liter, moles per liter, whatever it may be. And you can just, you could use an ice table for that situation. You don't necessarily have to, but you could find the concentration basically of each of the ions in that sort of solution and put it into the KSP expression and solve for the KSP. So you can kind of go either way on that. We also talked about things that do affect solubility, and there's a couple of things that really do affect solubility. One is a common ion. So much like we saw with buffers, if you do have a common ion, what it will do is basically suppress that salt from dissociating or breaking apart. So if we threw this guy in with some sodium chloride, that chloride there would be like adding chloride. It would cause the equilibrium to shift to the left, and it will keep that guy together, basically decreasing the solubility of the silver chloride, which in this case was very small to begin with, but it would decrease it even more. The other thing that we talked about that can affect solubility is pH. So I think we did, and that's where we ended last time with an example. I think it was like magnesium hydroxide maybe. And when we looked at magnesium hydroxide, which is somewhere here, which was this one I think we were looking at. And we calculated that basically using our ice table here, we could get the solubility of hydroxide. And from that, we were able to calculate the POH and then to the pH. And it was something like 10.45 or 46, depending on where you round it, I think. But basically, using sort of the KSP value, that was able to allow us to really calculate the pH of that particular solution. And what we know is if we sort of adjust the pH above or below basically that pH value, it will have an effect on the solubility. So if we basically lower the pH below that, say, 10.5 threshold, in order to do that, as we talked about, you would need to add an acid, which means you're essentially adding H plus. The H plus and the OH minus here would come together to make water. And what we would essentially be doing is removing the OH minus. Based on Le Chatelier's principle, that's going to cause the equilibrium to shift to the right, and it actually will increase the solubility of that salt by lowering the pH below 10.45. Again, as we talked about as well, you don't have to like drop it super acidic. You can even drop it to like a pH of 9, and you'll get probably a significant amount of that guy to dissolve more because it's less than sort of the baseline pH of that particular solution. Opposite would be true, obviously, if we brought the pH above sort of 10.45. To bring the pH above 10.45, we would need to add some hydroxide from a base. By adding hydroxide, that would essentially be creating a common ion sort of situation here. And it's going to cause the equilibrium to shift to the left. And essentially what will happen is it'll actually decrease the solubility of that salt. So again here, you would need to get it in this particular example above 10.45 to sort of see that more effective decrease in the solubility here. So especially when you have insoluble acids or bases, you could use your KSP and your KSP table to figure out sort of your baseline pH and what would happen if you kind of adjust the pH above or below that specific sort of value. Any questions on that there? Okay, so I think that is where we left off. So let us continue here. So let's talk about sort of maybe the third important factor here, which is in terms of solubility, and that's actually concentration. And it's the concentration of the ions in the solution. Earlier, we talked about Q, and a reminder that we calculate Q the same way as we do K. So Q in this case would be pretty much our products. And again, we could compare Q to the KSP, and if Q is greater than the KSP, we would expect a precipitate to form. If Q is less than the KSP, we would expect no precipitate to form. And really, if Q is sort of equal to the KSP, it's kind of a you basically have a saturated solution. So you're pretty much right at that point where you would see a precipitate form if you kind of did a little bit more to it. But technically, it would probably still be no precipitate at that point. So why don't we try one here? If we take 2 milliliters of 0.2 molar sodium hydroxide and they're added to 1 liter of calcium chloride, will a precipitate form? So the first thing you want to think about is, is there anything there that could make a precipitate? So basically, if we throw our sodium hydroxide into solution, we get these two ions. We throw our calcium chloride into solution, we get these two ions. So the question is, will these two guys make a solid? No. How about these two guys? Yes, so that is really the possible solid that can be made here. So that is what you really want to focus in on. So I'll give you some time here, basically figure out, will basically calcium hydroxide form in this particular case? There's a KSP for calcium hydroxide. So look, just calculate Q and see what you come up with here. Look, so again, here we'd want to calculate Q. So remember that basically we are looking at calcium hydroxide as our sort of only possibility, which would break apart into a calcium ion and a couple of hydroxides. The KSP here would be our calcium times our hydroxide, and we would need, again, to make sure we square it. Because of that, that also means that the Q here would be the exact same thing, our calcium and our hydroxide squared. So we basically need these guys' concentrations. And when we look at it here, really our hydroxide is going to come from our sodium hydroxide. And the concentration of sodium hydroxide here is 0.2. It is a 1-to-1 relationship, right? When sodium hydroxide breaks apart. So that means that the hydroxide concentration is also 0.2. But we actually need the concentration when they are mixed together, which means the concentration of hydroxide in this case would be 2 milliliters times our 0.2 molar divided by our total volume, which is 1,002 milliliters. I converted the liters into milliliters, so that's 1,000 milliliters plus 2 milliliters of the sodium hydroxide. So 1,000 milliliters from there, 2 milliliters from there is the total volume. That gives us a concentration for hydroxide here of, not that, 2 times 0.2 divided by 1,002 of about 3.99 times 10 to the minus 4 molar. Our calcium here is going to come from our calcium chloride, which once again, when calcium chloride breaks apart, we get a calcium and a couple of chlorides. It's a 1-to-1 relationship between calcium chloride and calcium, which means the concentration of calcium is 0.1 molar. Once again, though, we do need the concentration of calcium in the mixture. So that is 1,000 milliliters of the calcium chloride times the 0.1 molar divided by our total volume of 1,002 milliliters. And that gives us like 9.98 times 10 to the minus 2 molar. Any questions on that calculation there? So at this point, we have the concentration, obviously, of our calcium. We have the concentration of our hydroxide. So we can put it into our Q. So our Q here would equal our calcium, which is 9.98 times 10 to the minus 2. Our hydroxide, which is 3.99 times 10 to the minus 4. And we are going to make sure we square our hydroxide there. That gets us 3.99 to the minus 4 squared times 9.98 to the minus 2 gets us about a 1.6 times 10 minus 8 as our Q value. Any questions on that there? In this case, then, our Q is greater than, less than, or equal to the KSP. It is less than. Because it's less than, will we see a precipitate here? We will not, because it kind of goes to the product side, right? So no precipitate will form here. Any questions on any part of that calculation? So once again here, this is sort of the third factor that could affect solubility. You know, based on solubility rules, we should technically see a solid when you put these two guys together. But because the concentration of the ions were not enough, basically, are correct, we actually will not see a solid form. So those three things are really big factors, as I mentioned, as to whether or not you may see sort of something follow the solubility rules. pH, common ion, and the concentration of the actual ions that are in solution. Again, if they get too small or too dilute, you may actually not see the solid form. And that goes with anything, even, you know, something like silver chloride or something like that. You know, if you really have a bad concentration of each of those in the solution, you may not actually see the solid form. Any questions on that there? Remember, the other thing we talked about is that we can use the KSP values in certain situations to help us decide which salt would be more soluble than another. Remember, you could use that in a situation where they do break apart into the same number of ions. If they break apart into different numbers of ions, you cannot, again, use the KSP values directly to compare solubility. So that is sort of what we're going to kind of look at here. So what we're going to look at in this particular example is the idea of sort of selective precipitation. And it's a very common use of KSP, is that we want to maybe selectively precipitate out one ion from solution while keeping another one still maybe floating around. Now, the reason you might want to do that is for this particular example here, let's say we had basically a solution that had bromide ions floating around and chloride ions basically floating around. And you decide, I would like to precipitate out those ions as silver chloride or silver bromide based on solubility rules, right? Chlorides, bromides are soluble in everything except for silver, lead, and mercury. So if you decide you want to add silver to this to bring them out into silver chloride or silver bromide, they will precipitate out. Now, in these test tubes here, the guy on the right there, I think, is silver bromide. The guy on the left is silver chloride. They're essentially both white solids, which means that if you just sort of dump your silver ion into that beaker and you get some white solid that comes out, you have really no idea. Go like, I think this little part of the white solid is the silver chloride. I think this part is the silver bromide. You know, there's no way to exactly Looney Tunes, I tell you. There you go. There's no way to basically determine which one is which. So what we want to do in this case is maybe just take out one ion at a time. That way we know that what we are seeing is the ion we expect it to be, and wait and then take out the other ion. So this again is what is sometimes referred to as selective precipitation. And again, that allows you to really take out each one individually. It's a common sort of practice used, as I was talking about, in qualitative analysis sort of experiments, where basically the whole goal of those type of experiments are you basically have a beaker full of just ions floating around and you want to kind of take them out almost one at a time or in groups of ions. So the two that possible solids, obviously, that we could form in this case is silver bromide and silver chloride, which we could find our KSP values, obviously, from the table. So in this problem, what we want to do is figure out what concentration of silver we would need to add to that solution to only take out basically the silver bromide. So the goal here is to add silver that will get this guy to drop out as a solid, but leave the chloride alone basically and allow it to continue basically just to float around. So we can actually use KSP values and expressions to help us do that. So if we look at the KSP sort of expression here for silver bromide, the KSP would be our silver times our bromide. And that equals 7.7 times 10 to the minus 13. Now, in this particular example, both of the ions that are floating around in that particular solution, both the bromide ion and the chloride ion, have a concentration of 0.02 molar. So we actually know the concentration of those ions that are basically floating around in that solution. So it makes this calculation relatively easy. We can basically take our KSP expression and solve for the silver concentration. And because we actually know the concentration of the bromide in that solution, we could put it in. And basically what that will tell us is 7.7 to the minus 13 divided by 0.02. We are going to get, we'll call it 3.9 times 10 to the minus 11 molar. So what does that number represent? that number represents what? That is the silver concentration to when I get to that number, what will happen? We will actually start to see the precipitate start to form. So that is the minimum concentration of silver that you need to actually start to see silver bromide start to come out of solution. So that number is the minimum. Let me zoom it in for purposes here. The minimum concentration of silver to get silver bromide to precipitate. So we know that if we get the concentration of silver to 3.9 times 10 to minus 11, we will start to see a white solid form. And we know that hopefully that white solid is silver bromide. How can we know that it is silver bromide? We could basically do the same calculation for silver chloride. So if we do the KSP for our silver chloride here, which would be our silver ion and our chloride ion, this will equal 1.6 times 10 to the minus 10. Solving for the silver concentration in this case would give us 1.6 times 10 to the minus 10 divided by the chloride's concentration. 1.6 times 10 to the minus 10 divided by 0.02 is going to get us 8 times 10 to the minus 9 molar. So this number represents the minimum amount of silver concentration needed for silver chloride to precipitate. Which one is larger, the one amount needed for silver chloride to precipitate or the amount of silver needed for silver bromide? Yeah, the amount of silver needed for silver chloride is larger than the amount needed for silver bromide. That's why the question asked that. What that means is if we take the silver concentration and we get it greater than 3.9 times 10 to the minus 11 molar, we will start to see some white solid come out that is silver bromide. And we can be very confident that it is silver bromide because that is not enough silver to get chloride to come out of solution. We could continue to add silver at that concentration. We could continue to add silver above that concentration. I do just need to keep the silver below what number? I need to keep the silver below 8 times 10 to the minus 9 molar. So as long as I keep it below that number, any white solid that I see come out, I could be very confident should be silver bromide. You would do this, you would keep adding the silver until basically you do not see any more white solid come out, right? And that would tell you that you have probably precipitated out almost all of the silver bromide. At that point, you then could increase the concentration of silver to this or higher, and you will once again start to see some white solid come out. And that white solid, again, in this case, you could be very confident should be the silver chloride that's basically precipitating out. So by keeping the control of the silver ion in this example, we could selectively take out one ion basically at a time and know which one we have that we've taken out of solution. Any questions on that there? So this is another advantage of KSP. You could use really the expression to find the minimum concentration of the one of the ions that you need to allow precipitation to occur as well. Any questions? Is this what we expect based on the KSP values? So when we look at this guy and this guy, he breaks apart into 2 ions, he breaks apart into 2 ions, which means we can directly compare the KSP values to see which one is more soluble. The one that has a smaller KSP value is the silver bromide in this case, right? So smaller KSP value means it is less soluble, and this this basically agrees with our calculation here. We would expect the bromide to come out of solution first because KSP value is smaller. The silver chloride's KSP value is larger, which means it should be more soluble. And once again, here we can compare the two because they both break apart into basically 2 ions each. Any questions on that there? By the way, that highlight was green-ish, and I'm writing in red pen. Looks exactly like what it looks on my screen. All right, any questions on any of that there? All right. So that's a really important sort of aspect of KSP is just selective precipitation. And although, again, as I mentioned, we really don't do these type of experiments anymore, that is what this table is about. There are ions that are basically broken up into groups, and this is what is known as qualitative analysis. And basically, they're broken up into groups not based on the periodic table groups, but based on solubility. So things that are similar in sort of solubility rules. So for example, group 1 here is silver, lead, and mercury. And that is basically your chlorides, bromides, iodines, exceptions that make solids. And the way we precipitate out group 1 is you add HCl, which is a source of chloride. And basically all group 1 ions will come out as solids. They all come out as chlorides. That allows you to separate them out for our group 2 guys and our group 3 guys. Now, group 2 and group 3, they actually use the same sort of precipitating reagent. It's what is sometimes referred to as the group reagent. It is hydrogen sulfide gas, which you've ever used. Smells really bad because it's sulfur. So be happy you don't do these experiments there. But they actually use the exact same precipitating reagent for each of those groups. So everybody in group 2, ions, everybody in group 3. The difference, though, is one is done in acidic conditions, really acidic conditions, like 0.5 pH, and one is done in basic conditions. So that also illustrates what we saw earlier by adjusting the pH, and the pH has an effect on solubility. By making it really, really acidic, what that does allows only the group 2 guys to come out, but it allows the group 3 guys to still stay floating around. Then when you turn it basic, that is enough to make those group 3 guys basically come out of solution. So as we talked about, you know, kind of the pH has a really good effect. Then there's groups that are basically at the end there, which are pretty much soluble in anything. And a lot of times we rely upon everybody's favorite thing, flame tests and stuff like that, to identify those guys, because they really will not precipitate in a lot of cases. Although you can get, say, sodium and potassium to precipitate if you use the right reagent. But a lot of times we do something like flame tests. That's what you would have looked like if you did this type of experiments, but you don't. So we won't. All right. Any questions on KSP? The next thing that we're going to talk about is another type of equilibrium, and it deals with complex ions. So complex ions are usually a metal in the middle, a lot of times a transition metal, and they have a group of either ions or molecules that are attached to them, and those things are what are referred to as being ligands. So for example, here, in this case, we have a cobalt in the middle, and attached to it is 4 chlorides and a complex ion where the overall thing here has a +2 charge. Now, because of this, it will set up an equilibrium. So we have our metal and this guy right here, which is referred to as a ligand. And most ligands are Lewis bases. And we remember Lewis bases are things that do what? Not everybody at once scares me. Electron pairs donated. So a Lewis base is something that will donate a pair of electrons, while a Lewis acid is something that will accept a pair of electrons. Lewis acids are basically electron deficient. Lewis bases have more electrons to give. Good Lewis bases are things that have negative charges, things that are polar and have non-bonding electrons, like on their central atom. Those are good things. This will set up an equilibrium, which we could write to add to our ever-growing list of Ks. This is Kf, which is the equilibrium constant for a complex ion. And it's done the same way. It is products over reactants. And in this particular case, as the Kf value increases, so does the stability of the complex ion. That is because as the K value increases, we have more products. And more products means we have our complex ion, more of that there. So it basically will stabilize that guy. So here's a couple of cobalt sort of complex ions. Depending on the ligand, this is water, which is a good ligand. This is chloride. There are some differences, obviously, in the characteristics of those. Although on this screen, I'm not sure you could tell the difference, but that is pink on the left. Oddly, this guy right here is pink. This guy is blue. Does it look opposite from my direction? Or maybe I'm wrong. In terms of what you see in terms of the color there. Water is a good ligand because if you draw water, it looks like this, right? It is polar. It's got some non-bonding electrons happening there. And chloride, obviously, in order to become chloride, had to gain some electrons, right? So it's got that negative charge. So those are guys that have electrons to sort of donate. So they're really good ligands. NH3 as well is another really good ligand. NH3 looks something like this, right? It's also polar and got those non-bonding electrons up on top. The number of ligands attached to the central atom, the number of sort of atoms directly attached to the metal is what's known as a coordination number. So cobalt with 6 waters has a coordination number of 6, and that's because each of the water molecules are basically attached via the oxygen here. So that basically is 1, 2, 3, 4, 5, and 6 for the coordination number. Same thing with the chloride. Obviously, the cobalt is attached to each of the chlorides. So you may think that the coordination number is always basically how many of these ligands you have. And as we'll talk about in a later chapter, that's not always the case. There are certain ligands that actually could attach in multiple places per molecule. A common one is oxalate, which looks something like this. And basically to the metal, each oxalate molecule could actually attach in 2 places. Is what's referred to as being bidentate. It could actually attach in both places, which means if you actually had 2 of those oxalates, you would actually have a coordination number of 4. 1, 2, 3, and 4. So even though you have 2 oxalates, because each one can attach in 2 places, you double it and you get a coordination number there of 4. We'll talk more about that in a later chapter when we talk really more about how to name complex ions and stuff like that, and a little bit more about those things. But it's, again, just not always how many of those ligands you have. It is, if it is what is referred to as a monodentate, like water, pretty much all these guys here are monodentate, which means they attach in 1 place per molecule, which means the coordination number will be equal to how many there are of it. Now, ligands, they actually do add 1 at a time. So kind of like hydrogens, when diprotic, polyprotic acids lose hydrogens, they lose it 1 at a time. These ligands are actually added on 1 at a time. So if we look at the cobalt example, the first thing that would happen in this particular case is our cobalt would actually pick up 1 chloride, and you would get COCl plus. And then what would happen is the COCl plus, these are all aqueous, by the way, would then pick up a second chloride and make COCl2. Then the COCl2 would pick up the third chloride, which will make COCl3 minus. And lastly, the COCl3 minus will pick up the fourth chloride. And you'll get your COCl4 2 minus here in this case. Each of these ligands being added on will create an equilibrium, and you can have a K value for each of these steps along the way. Right. Now, if I decided to add up all these steps together, this guy and this guy would cancel, this guy and this guy would cancel, this guy and this guy would cancel, and I am left with CO2 plus 1, 2, 3, and 4 chlorides, basically making my guy down here my COCl4 2 minus. Yeah. If I wanted the KF for that guy, how would I get it if this was the information I was given? What do I do with all these K values? Add them, subtract them, multiply, divide. The right answer is in one of those answers I just gave you. Yes. That's a 25% chance. It is multiply. Thank you. So we would actually multiply. Remember, when you take K values, you multiply them together to get the overall one when you add them together. Yeah. Any questions on that there? All right, so let's take a look at this problem here, and let's talk about some special things that we do in these type of calculations. Typically speaking, the KF values for most complex ions, unlike KSP, are actually on the other end of the spectrum. They're actually very large values in most cases. So unlike KSP, where they're really small, a lot of times KF values are very, very large. And that affects the way that we approach these type of problems. So in this case, we're going to take 0.2 moles of copper 2 sulfate. We're going to mix it with a liter of 1.2 molar ammonia. What is the concentration of copper 2 at equilibrium? In this case, we're just going to assume, to keep everything sort of simple, everybody is still 1 liter in this case. Won't always be the case, but in this case, we'll do that. So what we're going to do here is find our arrows. There we go. That's good. And we're going to do an ice table. And what we want is the basically initial concentrations of everybody sort of in that mixture. So in this particular case, we're going to assume that this is going to be 0.2 molar. This will be 1.2 molar and 0 in this particular case. Now, one of the things that we do when we do these type of problems is we're going to make an assumption that because of the K value, which in this case is 5 times 10 to the 13, that is a very, very large K value, which means when I reach equilibrium, should I mainly have reactants or products? I should mainly have products, yeah, for sure. And that is very large, this value, which means even though it is a reversible reaction, we could assume that pretty much in this first case here, that is pretty much all going to make our product side. With that being said, our limiting reagent in this case would then be which one? It is going to be the metal. So the first assumption that we make in these type of problems is because the KF value is so large that pretty much all the metal will be the limiting reagent, and it's all going to get tied up with the ligands that are present. So what that means is when we get to the change part, we actually know what the change is going to be. It is going to be the concentration, in this case, of the copper, which is the metal. This would be then minus 4 times 0.2. And this would be plus 0.2. Why did I do the 4 here? For the coefficient. So this is kind of equivalent to doing 0.2, 1.2, and 0, minus x, minus 4x, and plus x, right? So because we already know what x is, we're just going to put the numbers in. So that is, again, basically what we did here. And the coefficients on the other two are 1, so we don't have to worry about it. So we already kind of know what the change is, so we're just going to do that. We still need to, again, take those coefficients into account. That means when we get to the end here, we're going to have 0 of that guy. We're going to have 1.2 minus 4 times 0.2. Going to give us 0.4 and 0.2 molar at this point. Any questions on that there? Now, obviously, in this case, we are looking for the concentration of copper at equilibrium, which means if the answer is 0, it wasn't much of a problem, I'm assuming, right? So in this particular case, although we zeroed out our copper in this case, it is still an equilibrium, which means some of it is going to work its way back the other way, even though almost all of it is going to the product side. That means what we're going to do now is kind of call this X, and we're going to come back and solve for it. So what we're going to do is use our KF expression, which in this case would be our products. Over our reactants. And again, that would equal our 5 times 10 to the 13. Putting in our values there, we end up with 0.2 up on top. We end up with X, which is our concentration of copper. And we have 0.4, which we still need to cube in this case. So at this point here, we're going to solve for X. So basically what happens is the X and the KF value switch places. And let's see here what we get maybe here. Divided by 5 to 13, divided by 0.4 fourth. We end up getting about 1.6 times 10 to the minus 13 molar for the concentration of free copper 2 in that solution. First off, any questions on the calculation part there? So the one assumption that we make here is pretty much based on the KF value. It is so large that it all should really be going to the product side. Pretty much all the metals should be tied up in that complex ion because they are definitely favored. So when that copper and that ligand get together, they want to come together to make that complex ion. The second part of the assumption is the amount of free metal ion should be really small. So does our calculations show that the amount of free copper is really small in this case? It is extremely small. It is like really not there, right? It's like there 12 zeros and a 1. Yeah, so there's really not much of the free, right? It's pretty much all tied up in that metal, but there's still a smidge of it technically floating around in solution. So those are the two major assumptions that you make when you do these type of problems. Because of the K value, all the metal will get used up, but some of it will come back. And if you do solve for the amount of free metal ion in solution, it should be a really, really small amount that is left. Any questions on that part there? So here, if you were to calculate the copper ion concentration, and you got a large number, something probably went wrong there in this case. So any questions on that one? All right, I tried one, you try one. All right, do this one here. We want the concentration of everybody, pretty much. In a solution that's prepared by mixing 150 milliliters of 1 × 10⁻³ silver nitrate with 200 milliliters of 5 molar, a little sodium thiosulfate, maybe. The stepwise formation is given below. We're looking for the concentration of everybody. We are not keeping any volumes constant here, so you need to figure out volumes, correct concentrations when they're mixed together. Give it a go, see what you come up with here. Okay, let's take a look, see how you're doing. So in this particular example here, we're looking for pretty much the concentration of everybody. So silver, kind of our intermediate, our complex ion. We're going to get it by mixing basically silver nitrate and a little sodium thiosulfate. In this particular case, we're actually given the stepwise sort of formation here of our complex ion. Again, the ligand, which is this guy here, coming on basically one at a time. And again, there's an equilibrium constant value for each of those steps. So a couple of things we could do here to begin with. We can get the overall reaction of what's going on by adding both of those guys together. So we can take basically both of these guys here and just add them together. In this case, this guy and this guy would cancel, and that would leave us the overall reaction, which is a silver ion plus a couple of our ligands here, making our complex ion, which is this guy. In this case here, we could get the K value for this by, again, multiplying the two K values above. And in case you wanted to use this value, it would be 7.4 to the 8 times 3.9 to the 4th here. So that gets us, I don't know, we'll call it 2.9 times 10 to the 13 in this case. First off, any questions on that so far? Now, we are going to need really, if we use this overall reaction, which we should, we are going to need the concentration of the silver ion that was put in there. And we will also need the concentration of the ligand that was put in there. In this case, we are mixing two different solutions. The silver is going to come from the silver nitrate. It's going to be really the source of the silver, which means when we put them together, the silver concentration will result from taking basically 150 milliliters of the silver nitrate times the concentration of the silver nitrate divided by our total volume in this case, which is 150 milliliters plus 200 milliliters. Well, that would be 350 milliliters would be our total volume. Milliliters will cancel. That's going to leave us with molarity. That will give us 150 times 1 to the minus 3 divided by 350 would tell us that our sort of opening silver concentration, we'll call it 3 times 10 to the minus 4 molar here. Any questions on that there? And actually, in this case, we'll take a couple of digits so we won't round so much. We'll take it to here we got 4, 3, 3. So we'll do actually 4.29 times 10 to the minus 4 molar. Now our ligand is going to come from here, and when that breaks apart, you basically get 2 sodiums and 1 of the ligands, which means the concentration of the ligand is still going to be 5. So that means that our ligand here, which is our S2O32 minus, will be 200 milliliters times 5 molar, which is the concentration of it, divided again by our total volume, which is our 350 milliliters will cancel, giving us 200 times 5 divided by 350. Going to give us a 2.86 molar as our concentration of our ligand. Yeah. You don't in this case because this is basically M1 V1 equals M2 V2. So technically speaking, when you did we'll just look at the units. When you do the top part here, times this and this. When you do the multiplication of the top part, what you get is not moles, but you get millimoles. And then when you divide it by milliliters, the millis cancel out, and that leaves you moles per liter, which is the molarity. So you can do it that way. You could absolutely convert it to liters. You would it would come out the same in this case for the molarity. So when you use something like basically what we're using here, right, is M1 V1 equals M2 V2. So when you use this equation, if you want to convert it to liters, you can the volume, or if you want to leave it in milliliters, it works out okay in this equation. If you are using volume and molarity by itself, not in this equation, just volume and molarity, it does definitely have to be converted to liters because you're probably looking for moles and not millimoles. So if you leave it in milliliters, you'll have millimoles. You'll be off by a factor of 1,000. So yeah. But yeah, you can definitely convert to liters if you want. But definitely if it's alone molarity and volume, definitely convert it to liters for sure. Other questions? Okay, so now we have that. We're going to we'll do our little ice table like we did before there. So we'll flip a page here maybe. So taking our overall reaction here, which was a silver ion plus a couple of these ligands. Making our complex ion. So initially there for our silver, I believe we had 4.29 times 10 to the minus 4. For our ligand, we had 2.86 and we had 0 of this guy. Once again, because this is a complex ion and we calculated our KF value there, it is really large. We will make our assumption that, again, all of the metal will be used up here in this part of it. So the change part, once again, is going to be the silver ion in this case. So the change here would be minus 4.29 times 10 to the minus 4. This will be minus 2 times 4.29 times 10 to the minus 4. Once again, for the coefficient. So we got the right stoichiometry. And this would be plus 4.29 times 10 to the minus 4. That means when we reach equilibrium here, that's going to be 0. This will be 2.86 minus 2 times 4.29 to the minus 4. Going to give us still 2.86. And this would be 4.29 times 10 to the minus 4 molar. First off, any questions up to that point? Now, from this very first ice table here, we actually have a couple of answers we're looking for. We have from this first ice table, we have the concentration of S2O32 minus is 2.86 molar. We also have the concentration of our complex ion at equilibrium, which is 4.29 times 10 to the minus 4 molar. So we basically have this guy's concentration. We have this guy's concentration. So we're really looking at this point for 2 other concentrations. We're looking for our intermediate, and we're also looking for the silver concentration. So at this point, there's a couple of different ways that you could approach this. And we'll talk about kind of both ways, and they should get you to the same spot depending on whichever way you choose. Because they actually gave us these K values in sort of a stepwise fashion, if I just look at K2 here, I pretty much have everything there except for the intermediate, which is one of the things I'm looking for. So one approach that you could do at this point is actually just use the K2 reaction and expression, and you could find that missing intermediate at this point. So that's what I'm going to do. I'm going to use K2 to basically find the concentration of this guy here. Because that second one is in equilibrium, you could write an equilibrium expression for it. So the equilibrium expression for K2 is the concentration of our complex ion divided by the concentration of the intermediate, which is sort of what we're looking for in this case, times the concentration of our ligand. And that equals 3.9 times 10 to the 4. And the nice thing about this is I have everything I need. I have this guy's concentration above. I have this guy's concentration. So I could put that in. So that guy from above is 4.29 times 10 to the minus 4. We are looking for this guy's concentration. And the next guy, which is our ligand, is 2.86 at this point. Yeah. Basically, these two guys are going to switch places, basically, when you rearrange it mathematically. And that means that our intermediate concentration would equal 4.29 to the minus 4 divided by 3.9 to the 4th divided by 2.86. And that will give us 3.8 times 10 to the minus 9 molar, which would be our intermediate. Any questions on that? So just so we're clear, I am using this reaction and K value to get this. So that is again why S2O3 is not squared or anything like that, because I am not using this equation. So I'm using the guy on the bottom. Any questions on that there? Now, if you took this approach, what that now gives you is the concentration of this guy, which if I look at my K1 sort of reaction, I now have the intermediate, I have the ligand, which means if I wanted to solve for silver, I could use the first reaction and the first K value as well. So that is what I'm going to do. So I'm taking now just the first one there, which is silver and our ligand. So our silver plus our ligand there, which is S2O3 2 minus. 2 minus, going to make Ag. Ag S2O3 minus. And again, this is the K1 expression, which means I do want to use the K1 value here, which is 7.4 to the 8. 7.4 to the 8 there. All right, so using this guy here in our KF for this would be our products divided by our reactants. And again, this would equal K1, which is 7.4 times 10 to the 8. Once again, we are looking for the silver concentration. So we do have the intermediate, which we just calculated. That was 3.8 times 10 to the minus 9, I believe. We are looking for the silver here. And this guy is still 2.86. Once again, mathematically speaking, these two guys are basically just going to switch places. And that would give us that the silver here would equal 3.8 to the minus 9 divided by 7.4 to the 8 and divided by 2.86 gives us a silver concentration of 1.8 times 10 to the minus 18 molar here. Any question on that there? By the way, the assumption that we make when we do these problems, large K value, right? Everybody should go to the right-hand side. The second part of that assumption is my free metal ion should be a large or small value. Small, and this is a small value, very much small value. So this is one way that you could approach this problem where you kind of use each of the individual steps, since they're all equilibrium sort of constants and they're all equilibriums and you have equilibrium concentrations, you could put them into each one individually. The alternative approach, which maybe some of you took, was after you did the first table there where we added it together, we had our silver plus our couple of these guys, making our complex ion here. And we got the K value for that guy, which was, where do we got? 2.9 to the 13, right? And when we got to the equilibrium line, right, we had 0 of this guy. This was 2.86, right? And was that 4 point something, that one? That was 4.29 times 10 to the minus 4 molar. So at this point, you could have went into the K expression for the overall reaction, which would give you, and it's the kind of the nice thing about equilibrium things, you could kind of do it at any point here. In this case, we would square it because of the coefficient. This would equal our 2.9 times 10 to the 13. Putting in our numbers here would give us 4.29 times 10 to the minus 4 divided by the silver concentration and our 2.86 squared. Once again, these guys would switch places. And if you do the silver at that point, you really should get the same number above, but let's just make sure. 4.29 to the minus 4 divided by 2.9 to the 13 divided by 2.86 squared gives you 1.8 times 10 to the minus 18 molar. So obviously you get the same answer. At that point, you would need to go into either the first reaction or the second reaction to get the intermediate like we did. So you definitely could have went that way and kind of worked your way backwards after you got the silver concentration, or did like what I did, kind of worked silver to the end. Either one should work out fine, as you can see here. Any questions on any of those steps there? Got one more to look at here in this chapter, and we're going to look at it here together and kind of talk about this type of problem here. So we've talked about sort of complex ions and KFs in the last couple of problems. Earlier, obviously, we talked about solubility and KSP. So this one sort of mixes the two together, and we're going to look at it. So in this particular problem, we're looking to calculate the molar solubility of silver chloride in 1 molar ammonia. And we have two sort of equilibriums given to us. One is a KSP equilibrium, which is our silver chloride breaking apart into the silver ion and the chloride ion. And we have our KSP value of 1.6 times 10 to the minus 10. The next one is actually what happens here is complex ion formation with silver and ammonia, which is a very good ligand, and makes this complex ion here of our silver complex ion, our diamine silver 1 ion here, and it has a KF value of 1.5 times 10 to the 7. So we're looking for what is the solubility of it in 1 molar ammonia solution. So we could kind of start this very similar to what we did in the previous problem. We do have two sort of equilibriums given to us. We could add these together. And when we add these together, in this case, the silver ion is actually going to cancel. And when it does, it leaves us really what we're kind of looking for in this problem, which is if I take some silver chloride and I add some ammonia, I will make this complex ion and some chloride, right? Now, does it matter if it's a KSP and KF? If I add them together, it doesn't, as you see. Does it matter if it's a KSP and KF if I want to figure out my K value? It doesn't matter either. They're all really equilibrium constants, right? It doesn't really matter if they're Ka, Kb, C, D, whatever you want to call it. They're all equilibrium constant values, which means you can multiply them together. Again, it's really kind of the same idea as what we do with Kw, right? Kw equals Ka times Kb. So, this is just a KSP times a KF. They're both equilibrium values. So it doesn't really matter. So you definitely can multiply them together. And we could do that to get our K value for this guy. And again, our K value would be multiplying the KSP in this case times the KF value in this case. And when we do that, we will end up with and again, remember that we are multiplying these guys together. 2.4 times 10 to the, I think it says -3, I think. Yep. Any questions on that so far? So what we got going on here is an overall reaction that's going to occur. It really does sort of express what we're looking for, which is what is solubility of the silver chloride when we add ammonia to it. So I'm going to start with that. So I'm going to rewrite our equation here, which in this case would be our silver chloride plus our couple of ammonias, giving us our complex ion and our chloride in this case. And once again, the K value there, 2.4 times 10 to the -3. So because we are looking for really the molar solubility in this case, that is going to lend us to doing a more of a KSP type problem, right? So KSP is about solubility. We're looking for the solubility. So that is how we're going to approach this ice table, is more of a solubility type problem. So initially here, though, we do have a concentration of ammonia, right? It's really the only number given to us, which is 1 molar. This guy would be 0. This guy would be 0 as well. So molar solubility, right, is represented by S. So in a weird case, in this case, because we're kind of mixing a couple of things together here, we actually will have a -2S here, right, because of the solubility there and the coefficient. This will be plus S and plus S. A reminder again, right, S is the molar solubility, right? So at equilibrium here, we will end up with 1 minus 2S, S, and S. Any questions on the ice table here? I'm not doing anything with the silver chloride because it is even though technically speaking, that is what we're looking for, but we're not going to obviously do anything with it in terms of the calculation part. At this point, we're going to do it just like a normal sort of KSP sort of problem. We're going to put this into our expression for K, which in this particular case, our K expression would be our complex ion. Times our chloride divided by our NH3. And once again, we want to make sure that we do square it because of the coefficient that we have in the actual balance equation. And that's going to equal our 2.4 times 10 to the -3. Putting in our values here, we're going to get S times S up on top divided by 1.0 minus 2S, and it is going to be squared as well. At this point, we're going to solve for S, and I think just looking at it, I could put a big square root on both sides, yeah, and we're going to be okay in this case. So when we square root both sides, that will give us an S up on top. That will give us 1 of the 1 minus 2S on the bottom. And the thing I usually forget to do, which is take the square root of that other side. So let's do that. Square root of 2.4 to the minus 3. Going to get us 4.899 times 10 to the minus 2. We're going to multiply this guy to the other side. And when we do that, we end up with 4.899 times 10 to the minus 2 minus 9.798 times 10 to the minus 2s is equal to s. Yeah, we're going to add this guy back to the other side. That's going to give us 4.899 times 10 to the minus 2 is equal to, that is basically 1.0979 times 10, no times 10, s. And that means that we're going to divide it back to this side, and that will finally give us here 4.5 times 10 to the minus 2. This is S, which is the molar solubility, right, of silver chloride. Once again, it would be this S, which is a 1-to-1 relationship back to that guy. So it's the same thing. It's also this S, which is a 1-to-1 relationship back to that guy, which would give you the same thing here. For a reference point in terms of grams, if we did the molar mass there of silver chloride, silver is 107.9, I think, right? Chlorine is 3545. So if we take 143.35 grams per mole, this would basically be moles per liter, right? We will times that by 4.5 to the minus 2 is something like 6.45 grams per liter. Yeah. First off, any questions on that calculation? Say what? I'm sorry. It is. So technically, even though we wouldn't do it here, this basically would be minus S. So basically be S over here. So this is equal to S because, again, that's basically what S is equal to. And that is a 1-to-1 coming backwards. So it's basically the same thing. Yeah. It's both. It's actually, it's the constant, it would be the concentration of the complex ion at equilibrium. So it would be this guy's concentration, equilibrium, and molarity. It would be the chloride's concentration at equilibrium, and it also would be the concentration of silver chloride at equilibrium as well. Because technically you would kind of zero, right? This would be kind of minus S and like BS, you know, even though you wouldn't put anything in there. So it's basically a 1-to-1 relationship. So as we talked about earlier, kind of when you solve for S in these type of tables, even though technically it really is sort of the molar solubility of those ions at equilibrium, it also is sort of the molar solubility of the whole thing. It kind of works out always to be the same number, because as you go backwards, you're either, you know, 1-to-1 relationship, or if it was, say, a 1-to-2 relationship, you would then divide the two as you go backwards and then become the same thing as S, basically. Yeah. Now, for reference, any other questions on that? For reference point here, if we took just our one that we did earlier, which was earlier on this calc in this chapter, which is if we took silver chloride and water, this would give us, as we did earlier, 0, 0. Change would be plus S plus S. This would give us S and S. That would give us that basically S squared is equal to the KSP. Taking the square root would give us the molar solubility of silver chloride in water, as we did earlier on. And we ended up with something like 1.3 times 10 to the minus 5 moles per liter, right? Which is much less than that. And if we times this by our 143.35 grams per liter, we ended up with basically 0.0018 grams per liter. So that is the solubility of silver chloride in water, pure water, that we did earlier, basically 0.002 grams per liter. With the ammonia, it is about 6.45 grams per liter. It is more soluble in the ammonia, right? And that is why the KF values are so large. Basically, when those metals get near a really good ligand, the formation of that complex ion is 100% favored because it will come together. We don't do this experiment, but part of the qualitative analysis experiment is you make silver chloride to verify that you had silver. You add ammonia and your solid disappears. It really doesn't disappear. It makes this complex ion right here, and it becomes aqueous. And the way you test that it really was there, you drop a bunch of really strong acid back in. And what happens is the acid's able to free up the ammonia and allow the silver and the chloride to come back, and you will see the solid reappear. So by adding something like ammonia to silver chloride, you could actually break it apart, take it out of the solid, because the conditions are so favored for that complex ion to form. It basically will extract the silver from the solid and make it into that complex ion that's aqueous in this case. So definitely, whenever you have that possibility of making a complex ion and a good viable ligand is there, a lot of times that is definitely favored, as we saw with our KF values in this particular table, or if not, if you look at this particular table, they are extremely large. A lot of them, like that's 35, 43. You know, they're pretty much, in the most cases, a one-way street. They're kind of almost all heading to the product side, but because it's still in equilibrium, it will come back the other way. And there's still just a smidge of the free ions left, but very, very small amount, because that complex ion is definitely very much favored. Any questions on KFs and complex ions? All right, that wraps up this chapter.